Annenberg Media.
Voyages to other planets require enormous energy. The amount of energy expended can be minimized by using the same force that moves the planets through the solar system. The force of the sun's gravitational field is used to navigate in space.
A few years ago, the only conceivable purpose for all of the beautiful celestial mechanics we've been teaching you would have been to plot the courses of the planets in the sky. But that's no longer true. Today, many of the objects up there were put up there, either by us or by our friends on the other side of this tiny planet we inhabit. And in a few years, if we manage not to blow each other up, there are sure to be many more. The routes followed by spacecraft and artificial satellites are governed by exactly the same rules that govern the orbits of the planets. And so, if someday somebody comes tooling up to you, opens the window of a spacecraft and says, "Hey buddy, how do I get to Venus from here?" I want you to know what to answer. You'll say, "I'll draw you a map."
Mariner 10, 1973, to Venus and Mercury. An exquisite vessel, a scientific explorer launched across the solar sea. Viking, 1975, to Mars. Another mechanical marvel launched in search of answers. Answers that may return to haunt long-held theories. Answers to such questions as, what was the biological spark that ignited the human species? Voyager, 1977. To Jupiter and to Saturn, to Uranus and to Neptune. Mariner, Viking, and Voyager. This century's Francis Drake, Ferdinand Magellan, Eric the Red, launched to discover how the planets were created. First-hand answers may turn current matters of fact into historical chapters of science fiction, or they may do just the opposite. But whatever the answers from outer space, first come the questions on Earth. Questions beginning with, in search of the unknown, how do they reach beyond the known? Without even the aid of a lighthouse, how can a modern mariner or any other space-age vessel sail from here to there? And once launched into the cosmic seas, who navigates? Caltech's Jet Propulsion Laboratory, JPL, Pasadena, California. Nerve center for exploration into the endless frontier of space. the cerebral cortex of NASA's unmanned planetary program, the Deep Space Network Operations Center. There are countless problem solvers in the space age, but only a few are qualified to solve problems in outer space itself. One age-old problem of outer space has to do with getting there.
I suppose it would be possible to fly a spacecraft on a straight line from one point to another in the solar system. It would require an exorbitant amount of propulsive capability. It surely is not the best way to do it. In fact, in flying from one place to another in the solar system, we use one of Kepler's laws, which tells us that the planets move around the sun on ellipses, and the spacecraft will follow exactly these same laws.
Ignition. Obviously, to aim toward the planets with brute force alone is to miss the point entirely. Clearly, present-day space navigators look to the future by way of the past. Kepler's 3 laws stated how the planets orbit the sun. Newton explained why Kepler's laws work. Now, no matter how futuristic the problems, space navigators use Newton's and Kepler's laws as operating principles.
The way we get a spacecraft from Earth to Mars is to put the spacecraft in an independent orbit around the sun that necessarily intersects the orbit of Earth and the orbit of Mars. In fact, the launch vehicle has to impart enough speed to that spacecraft right after launch so that it will coast all the way from Earth to Mars once the launch vehicle burns out 30 minutes after liftoff.
To travel between 2 points in space, a craft coasts to its destination in orbit around the sun, just as if it were an orbiting planet. The path of a spacecraft from one planet to another is called a transfer orbit.
For the Viking mission, we were quite limited in selecting the transfer orbit because Viking was the most massive interplanetary spacecraft ever launched. The then most powerful launch vehicle, the Titan Centaur, could just barely get us to Mars. The classical transfer between 2 planets is referred to as the Hohmann transfer. We followed a transfer very close to this. It's one in which we launch from Earth tangentially at the lowest point in the orbit, that is the point closest to the sun, and arrive at Mars at the highest point, the apoapsis point, the most distant point from the sun. So we have an orbit that just manages to connect from the Earth's orbit to Mars' orbit. In fact, the spacecraft does 1/2 a revolution in this orbit to make the transfer.
Getting there may be half the fun, but the trip can't just start any old time. No matter how elaborate the preparations, the whole crew has to wait until it's time for launch.
The problem of getting a spacecraft from one point to another in the solar system is rather like shooting at a moving target with a rifle. There are 2 parts to the problem. You have to be sure that the target is within range, and you have to establish the amount by which you're going to lead the target so that it doesn't pass you before you get there.
Just as Kepler's 3rd law fixes the length of an Earth year, and the length of a Mars year, it also dictates how long a spacecraft, coasting in an orbit of its own, will take to get from the Earth to the position of the orbit of Mars. It takes about 8.5 months. In order for Mars to be waiting when the craft arrives, it has to be launched when Mars is just 44 degrees ahead of the Earth. That alignment is called an opportunity.
In the planetary problem, we have to wait to get the planetary alignment to be just right, and within the limits of our launch vehicle capability, when the alignment is correct we have what is referred to as an opportunity, and this is when we can launch. Typically, these opportunities have a duration of 1 to 2 weeks.
Space navigators must wait for just the right moment, when a coasting orbit will take the spacecraft from the position of the Earth to the orbit of the target planet, just when the target planet arrives there. That moment is called an opportunity. And opportunity doesn't knock at the same time for all planets. Prospects look good for Mars about every 2 years. An opportunity to visit Venus presents itself every 19 months. And for Jupiter, each 13 months. When these times come, space navigators must be ready to move quickly through a launch window. A few fleeting moments each day when the rockets must actually be fired.
For each day, there is a fairly restricted time within which we could launch. This problem is quite similar to one where you might be riding on a carousel and playing catch with a friend standing off to the side. For each revolution of the carousel, you'd have a fairly short range of time where you could see your friend and could throw the ball to him. On our revolving carousel called Earth, the problem is very similar. Each time that the Earth comes around, we have an alignment between the launch site and the direction in which we need to depart from Earth. So the problem is one of waiting until we get this alignment, and then we launch.
The carousel called Earth is itself in a nearly circular orbit around the Sun. Any increase or boost in speed creates a bigger, more eccentric orbit. To go from an Earth orbit into a Mars transfer orbit requires a boost of exactly 2.9 kilometers per second. But the first task is to escape from the parking orbit around the Earth. A rocket thrust will boost the craft into a hyperbola that drifts to infinity at just the right speed of 2.9 kilometers per second. And the thrust must come at just the right moment. That moment is 7:56 p.m. local time. The Sun does the rest of the job, bending the trajectory into a Mars transfer orbit. If the destination is Venus rather than Mars, the basic idea is the same. But now the journey is inward, toward the Sun. Blasting off in the morning at 7:40 a.m., the craft escapes from the Earth. But this time, it's going backward relative to the Earth's orbit, losing speed and falling inward toward Venus. So, if someday someone does open the window of his spacecraft and ask you,
Hey, buddy, how do I get to Venus from here?
now you know what to tell them. Getting the craft into the planet's vicinity, making the orbits intersect, is only part of the space navigator's challenge. The object, after all, is to land the craft. In preparation to land Viking, an earlier mission, Mariner 9, took photographs to stake a visual claim on Mars. With preparations completed, Viking is ready to land. But Viking's cameras reveal a site that's surprisingly and dangerously laden with boulders. Fortunately, Viking has the ability to scout another landing site. But finding a safe site is one thing, actually landing safely, quite another.
In the atmosphere now. Delayed stream.
One false calculation, which is easy to imagine at a distance of 200 million kilometers, could add up to the destruction of Viking. But the pre-programmed computer on board Viking saves the day, to say nothing of the craft itself. So for the first time, the planet Mars is photographed from its own surface. Newton and Kepler might have fantasized about setting some sort of scientific gadget atop a distant planet, but it took JPL's scientists to do it. Scientists and engineers, by nature, don't tend to rest on their accomplishments. The space navigators set their sights not only on Mars, but on an enormous journey to the four outer giants of the solar system: Jupiter, Saturn, Uranus, and Neptune. In this case, timing is everything because these planets line up right. That is, right for one spacecraft to visit all four in the same trip, just once every 175 years. That 175-year cycle came around in 1977. In that year, not one, but two fragile vessels set forth on a journey that would take them to the giant planet Jupiter, then through the rings of Saturn. One of them would even pass by mysterious Uranus. Even beyond distant Neptune. And finally, both would coast into the endless reaches of interstellar space. To make the trip meant first of all overcoming gravity, just to escape from the planet Earth. But even then, and even given the grand once in 175-year opportunity, it still couldn't have been done without the help of gravity itself.
The principle of gravity assist is really pretty simple. What we do is we use the gravity of a planet to change the speed and direction of flight of a spacecraft as it goes past the planet. Now, of course, when I say change the speed and direction, I mean really with reference to the sun. From the point of view of the planet, nothing much happens. A spacecraft is out here approaching with a certain speed. It speeds up, whips around, and leaves. Same speed leaving as it had coming in. But from the point of view of the sun, it's quite different.
Both Voyager missions got their first gravity assist from the planet Jupiter, propelling them onward toward Saturn. But to appreciate the concept, it's not necessary to go quite that far.
You might think of it this way. Suppose you imagine a baseball game. Here's a batter, and he's going to bunt. So he holds the bat absolutely still. The pitch comes in, bounces off the bat, and down onto the turf and rolls away. The only thing that the baseball bat has done in this interaction is change the direction of flight of the baseball. Hasn't added any energy to it. But if the batter's swinging, the bat is moving. The bat has energy. When the bat hits the ball now, it adds quite a bit of energy to it, and in fact enough to get over the fence and be a home run. It's the combination of the energy which the pitcher gave to the ball and the extra energy the ball got from the swinging bat that is now enough to carry it over the center field wall. Of course, like most analogies, this one isn't perfect. A spacecraft doesn't bounce off a planet like the ball off of the bat. The spacecraft approaches the planet, and it's the gravitational pull of the planet that causes this interaction. It's not a physical contact.
If Jupiter really did hit Voyager, that would be the ballgame. While there's no physical contact, however, there is a striking connection between baseball and physics. Jupiter doesn't stand still. It moves. And like a swinging bat, it gives up some of its energy to the ball of Voyager as it flies by. Playing on the largest field around, the universe itself, space navigators hurled Voyager past Saturn and her fabled rings. And there, like mighty Casey at the bat, they came up against the unexpected.
The rings are actually a countless number of small bodies in orbit around Saturn. One of the surprises that we found, for instance, was that the two brightest rings, the A and the B ring, which can be seen from Earth and look rather smooth and homogeneous, when viewed up close appear to be quite structured. Perhaps the most intriguing surprise, though, was that associated with the narrow F ring, which is just outside of the A ring. The F ring was actually discovered in 1979 by the Pioneer 11 flyby. It's a very narrow ring of particles orbiting Saturn. We discovered with Voyager 1 an essential key to understanding the dynamics of such a narrow ring. We found two satellites orbiting Saturn, one just inside the F ring and one just outside the F ring.
The key to the mysterious F ring turned out to be the same principle that had gotten Voyager there to see it, the principle of gravity assist. The F ring and its shepherding moons are all in orbit around Saturn. Obeying Kepler's third law, the inner moon moves fastest, the ring material slower, and the outer moon slower still. When a ring particle encounters the faster-moving inner moon, the moon pulls it along, speeding the particle up and flinging it into a higher orbit. When a ring particle encounters the slower-moving outer moon, the particle gets held back, slows down, and falls into a lower orbit. These effects, together with collisions among the ring particles themselves, shepherd the material between the moons into a narrow ring. While this kind of motion was somewhat unexpected, its discovery wasn't a total surprise. Shepherding was offered as a theory before Voyager encountered Saturn to explain the rings of another planet.
When the shepherding theory was first proposed as an explanation for the narrow rings around Uranus, it was not universally acclaimed because it was an uneconomical theory. That is, that it required the presence of two unseen objects, two small moons, to explain the presence of one object, a narrow ring, which had been observed. I think the first direct evidence that such a shepherding effect took place was with Voyager. I think it was a surprise to many. It wasn't a surprise to those who believed in the theory.
Today, shepherding and gravity assist combine to illustrate that 300 years after the discovery of classical mechanics, there are still new discoveries to be made. Celestial scientists, from Johannes Kepler onward, could calculate the motions of the solar system. And any great scientist who understood the orbits of the planets held within his grasp a profound and truly heavenly knowledge. But for 300 years, even to the greatest minds, the heavens remained within reach of the intellect alone. 3 centuries would pass before the first hesitant steps beyond the barrier of Earth's gravity were taken, to finally allow scientists to take part in, rather than observe from afar, the worlds beyond the planet Earth. Navigating as well as calculating, making heaven passable as well as possible, that is the miracle of the space age. That's what the father of classical mechanics might have dreamed of. But that is what the space navigators made reality.
Of all the magnificent discoveries of the Voyager mission, one of the most unexpected and spectacular was the complexity of the rings of Saturn. When this discovery was made, scientists all over the world went scrambling around trying to find an explanation. And so far as I know, no one has succeeded. Well, I have a theory of the rings of Saturn. You can call this the Goodstein theory. But I haven't published it yet in a scientific journal, so you'll have to promise not to tell anyone, okay? First, let me remind you that the Voyager spacecraft, like the Pioneer 10 before it, is going to escape from the solar system and drift forever in the endless reaches of space. Now, there's just the tiniest chance that someday someone or something from an alien civilization will come across one of those craft. And just in case that happens, we've put on each craft a message from us to them. On the Voyager craft, among other things, the message has a phonograph record. It has music and samples from various languages and a greeting from President Carter and a number of other things that an alien civilization just couldn't do without. But the main point is this. We assume that if an intelligent being ventures into space and finds a flat disk with a lot of grooves in it, that they'll know exactly what it is and what to do with it. Well, the rings of Saturn are a flat disk with a lot of grooves in it. On second thought, I think I'll keep my theory to myself. I'll see you next time.
To navigate from the Earth to another planet, a spacecraft is launched into a transfer orbit. The launch must occur in a brief window during a special opportunity for each planet. Navigators also use gravity assists from the planets themselves to provide additional boosts.
Annenberg Media. For information about this and other Annenberg Media programs, call 1-800-LEARNER and visit us at www.learner.org.